Head to these springs in the hot Florida summers, mostly to cool off and relax, but there's more to them than what emerges at the mouth of the spring. I know because I've seen it.
Nothing looked different on the surface. Beaches were still full. Cities were still running. Water was still flowing from every tap, but nearly 1,000 feet below Florida, scientists were watching numbers they did not expect to see. Pressure readings dropping, recharge slowing, a system that had stayed stable for centuries beginning to shift. No alarm sounded, no public panic. Just quiet meetings between hydrologists, engineers, and water authorities asking one uncomfortable question. What happens if one of America's largest underground water supplies can no longer keep up with demand? How does a water system used by millions begin to show signs of stress without anyone noticing? And more importantly, if the warning signs are already here, how much time do we really have to respond? Carefully measured, because deep below Florida's limestone foundation lies one of the most important freshwater systems in North America, the Floridan Aquifer, a vast underground reservoir supplying drinking water to nearly 10 million people across several states, including more than 2 million in central and northern Florida alone. And over recent decades, scientists have been watching something very closely: gradual pressure on this underground system. Not collapse, not disappearance, but measurable stress. What exactly is happening underground? Why are water managers paying closer attention? And what does groundwater science actually say about the future? To answer that, we must begin with the science of aquifers themselves, because groundwater systems are often misunderstood. An aquifer is not an underground lake. It is not a cavern filled with open water. Instead, it is porous rock, limestone, sandstone, gravel layers. Water exists inside tiny spaces between mineral grains and fractures within rock layers. Think of it less like a cave and more like a saturated sponge. Under natural conditions, this system operates in balance. Rain falls, water slowly seeps through soil, gravity pulls it downward. Recharge replaces what is withdrawn. This process may take months, years, sometimes decades. Florida historically maintained strong recharge because of its climate. Regular rainfall, flat terrain, highly permeable limestone geology. For generations, this created one of the most productive groundwater systems in the United States, a stable system. But stability depends on balance, and balance depends on pressure. Over time, 3 pressures began influencing this balance: population growth, agricultural expansion, climate variability. Individually, none of these factors creates immediate crisis. Together, they create long-term demand. As Florida's population increased throughout the late 20th and early 21st centuries, groundwater withdrawals increased steadily. Municipal systems expanded. Irrigation networks grew. Industrial use diversified. Meanwhile, seasonal rainfall patterns became less predictable. Some regions experienced longer dry intervals between recharge periods. Scientists began noticing subtle signals. Water level monitoring wells showed gradual declines in certain areas, not everywhere, not uniformly, but enough to track. This was not sudden loss. It was trend detection under normal conditions. Groundwater pressure keeps freshwater separated from surrounding saltwater zones, especially in coastal regions. When groundwater levels decline, this pressure balance can shift slightly. This introduces one of the most important concepts in aquifer science: hydraulic equilibrium. When freshwater pressure decreases, saltwater can migrate inland through connected rock layers. This is called saltwater intrusion. It does not happen overnight. It progresses slowly, often measurable in inches per year, but it is carefully monitored because prevention is easier than reversal. This is one reason water agencies have increased observation programs across Florida. Not because collapse is imminent, because monitoring allows intervention. The discovery that attracted scientific attention was not dramatic. No wells suddenly ran dry. No cities lost supply. Instead, researchers observed measurable declines in certain monitoring zones compared to historical averages. In some localized test regions, water pressure levels were significantly lower than mid-20th century baselines. These figures are sometimes misunderstood when expressed as percentages. A 90% drop often refers to pressure changes at specific monitoring points relative to earlier measurements, not total water loss across the aquifer. This distinction is essential. Aquifers rarely disappear. They fluctuate. Understanding this difference separates scientific interpretation from headline simplification. To understand how aquifer stress develops, scientists often describe a simple three-stage pattern. First, increased withdrawal. Groundwater extraction increases faster than recharge in specific zones. Second, pressure adjustment. Water levels adjust downward locally as the system redistributes pressure. Third, stabilization or intervention. Management policies adjust pumping rates. Conservation programs increase efficiency, or recharge projects are introduced. Each stage is manageable when detected early, and detection is exactly what modern monitoring systems are designed to do. Florida maintains one of the most extensive groundwater observation networks in the United States. Thousands of wells continuously record water levels, pressure, and chemical composition. These are not emergency tools, they are diagnostic tools, like medical checkups for environmental systems. One major misconception about groundwater decline is that it means water is running out. Scientifically, this is rarely accurate. The more precise concern is sustainability of withdrawal rates relative to recharge rates. This is a management question, not a disappearance question. Another misconception is that aquifers recover quickly when pumping decreases. Recovery often takes time because groundwater movement is slow, measured in feet per day, sometimes inches. Aquifers respond on geological timescales compared to surface reservoirs. This is why long-term planning dominates groundwater policy. In Florida, water management districts have implemented multiple strategies designed to maintain system balance. Conservation incentives, water reuse expansion, seasonal withdrawal adjustments, aquifer storage and recovery projects where excess treated water is injected underground during wet periods for later use. These are not experimental ideas. They are established hydrological management practices used worldwide. The science behind aquifer behavior continues evolving. Modern researchers use satellite gravity measurements, isotope tracing, and 3D groundwater modeling to better understand subsurface flow patterns. These tools provide something earlier generations lacked: precision. For example, satellite missions such as GRACE Hive allowed scientists to detect regional groundwater mass changes by measuring subtle variations in Earth's gravitational field. Invisible water becomes measurable. This is why more groundwater stories appear today. Not because systems are suddenly failing, because measurement technology has improved. More sensors create more signals. More signals create more awareness. Looking ahead, scientists are watching several key indicators in Florida: recharge rates during wet seasons, urban demand growth, agricultural efficiency improvements, saltwater boundary movement. None of these indicators suggests sudden loss of supply, but they do reinforce the importance of careful management. Future planning may include expanded desalination support in coastal regions, increased reclaimed water use for irrigation, smarter metering technology, expanded stormwater capture, layered solutions. No single answer, because water systems are networks, and networks require coordination. Why does this matter beyond Florida? Because groundwater supplies nearly half of all drinking water used by humanity. Aquifer sustainability is not a regional issue. It is a global one. Regions from Spain to India to California face similar management challenges. Florida represents an important case study, a high rainfall region still practicing careful groundwater monitoring. This challenges another misconception. Water abundance does not remove the need for management. Even wet regions require balance. There is also economic importance. Stable water supplies support housing markets, tourism industries, agriculture, and manufacturing. Businesses rely on predictable water access. Water stability often equals economic stability. This is why aquifer monitoring rarely stops. It becomes permanent infrastructure. There is also a deeper educational lesson. Environmental change is usually quiet, gradual, technical. It appears first in spreadsheets, in monitoring charts, in long-term averages, not in dramatic events. Understanding environmental science requires patience with slow data. The Floridan Aquifer teaches this well. It reminds us that sustainability is not about reacting to emergencies. It is about maintaining balance before emergencies develop. So how should events like this be interpreted? Start with scale. Is the observation local or regional? Continue with time frame. Is the trend seasonal or multi-decade? Then context. Are management responses already in place? These questions transform concern into understanding. Florida's groundwater story is not one of sudden danger. It is one of continuous management, continuous observation, continuous adjustment. If there is a future challenge, it will likely involve balancing population growth with conservation efficiency. Technology will play a role. Smart irrigation systems, leak detection networks, advanced filtration reuse. These are not distant possibilities. Many already exist. If there is one takeaway from Florida's aquifer monitoring, it is this: water security depends less on how much water exists and more on how carefully it is managed, because even large natural systems require stewardship. If this kind of scientific environmental analysis is valuable to you, you may consider following future long-form documentaries in this series. Each explores real environmental systems, measured trends, engineering responses, scientific context, because understanding water requires more than numbers. It requires perspective. Beneath Florida today, water continues moving quietly through limestone channels carved over millions of years, drop by drop, pressure balancing across vast underground distances. No headlines mark this movement, no cameras record it, but sensors do, scientists do, engineers do. The system continues, not collapsing, not disappearing, adjusting, because aquifers are not static reservoirs. They are living systems of flow and balance. Above ground, rain continues to fall. Some runs to rivers. Some evaporates. Some begins the slow journey downward, becoming tomorrow's groundwater, a cycle older than cities, older than roads, older than memory. The real story is not loss. The real story is responsibility, and responsibility, like groundwater itself, moves slowly, but shapes everything it touches.